Hi. So in this video, I am going to be demoing my log distribution system plus the simulation stack, which is highly concurrent and has support for failure and recovery of analyzers. So this is how I'm going to do it. I'm going to do three different test cases for the system, explain how the system behaves and works, and towards the end, I am going to be explaining my architecture and the tech stack and what sort of technologies that I've used. So this is my front-end interface for interacting with the whole, like to start the simulation, load testing on the distributor, and to view the metrics on the analyzers. So the first step, as explained in the setup video, is to add analyzers to distributor so that it can start routing the packets to these analyzers in the ratio of the weight that is assigned to each analyzer. So here I have a button that does the auto assigning based on the Docker compose that I've configured. So here I have assigned analyzer 1, 2, 3, 4, 5, 6, and their weight is also 1, 2, 3, 4, 5, 6. So one message should be assigned to analyzer 1 for each 6 messages that are assigned to analyzer 6. And yeah, that's how ratio works. So this is the like the user swarm has started. They are like or like requests to route the packets to the analyzers. It has started. We are doing 900, 1000, yeah, a good number of requests per second here. We already have 20,000 requests, average response time. And as you can see in these graphs, that the ratio that we set for the weights is being followed. Analyzer 1 has 4,000, okay, at this point, Analyzer 1 has 4,000 packets, 2 has 8,000. And so it is following the 1, 2, 3, 4, 5, 6 ratio. Even with like messages per second and packets being routed, the ratio is being followed and it is clearly visible in this pie chart. Now I am going to simulate failure for Analyzer 1 and Analyzer 6. So yeah, so I have simulated failure. I got these nodes down and now only 2, 3, 4, and 5 analyzers are on, and whatever packets are coming to the distributor, they will be uh, routed to these analyzers based on the new distribution. So you can see that like 2, 3, 4, and 5 are active, and the ratio like we aren't routing any packets to 1 and 6, so the ratio is going to change now until these nodes come back up. So I'm going to wait for a few seconds so that we can see that the ratio is not what it was before, so that in the recovery stage we have better results on how it converges back to what it was in the start. Yeah, I guess that was enough time. So now we know that these nodes are following the new ratio of 2, 3, 4, 5, and nodes 1 and 6, like analyzers 1 and 6 are down. So I'm going to start them up again, and uh, this process is going to show that once the nodes are back up, the ratio will be brought to what it was before. So that is like 1, 2, 3, 4, 5, 6. So I have brought the nodes back up, and you will see that the messages per second being routed to the analyzers that were down is going to significantly increase and be more than what it is for other analyzers, because we want to bring this ratio to where it was before. So multiple messages are going to be routed to the node that was down so that we can fill up their quota. So as you can see, like the messages per analyzer, this is the cumulative graph, so it's increasing, and uh, approximately for 6 we have to bring it till here, and for 1 we have to bring it to somewhere here. So yeah, and we can observe that uh, like 1 and 6 are the analyzers which are being routed more number of messages, more than what we are routing to the other nodes. Now it still takes some time to converge to the actual ratio once the nodes are brought back up again, but it does, and that is what is going to happen here as well. uh, so key thing to note here is I think we have brought analyzer 1 back to its original place where it should be in the ratio, but analyzer 6 is way off from where it should be. So all the packets are being routed to analyzer 6 right now. There are like no packets or messages being routed to other analyzers. So this is going to happen until we actually reach the required ratio. So now like 5 and 6 have almost equal, but 6 should be more than 5. And once we have reached at the perfect ratio of like distribution, that is when the other nodes, like other analyzers, are going to start receiving packets or messages, and then it's going to function as it was in the start. So here you can see that the like we are at the equal ratio of what we said, and now the other analyzers are also being routed the packets or messages. We are at the normal functioning of the routing where based on what we observed at the start, where even the messages per second, like the rate was also in the ratio, and the messages per analyzer, like the total number of messages analyzed so far, is also in the ratio. So I guess that this is like a test to prove that the failure and recovery system for the distributor works. And I demoed this in this particular ratio to show that it works when ratios differ for each analyzer. Now I have auto added all the analyzers, and in this case, I'm going to do wait 1111. And this time, the difference in testing, what I'm going to do is I'm going to like use 10,000 connections to test on my distributor. So we can have 10,000 concurrent connections, and we'll see how what happens in this case. And I'll increase the hatch rate to 500. Right. So as you can see, the system does struggle a bit in this case. Uh, it has like I guess I'm still getting 700 RPS. That's probably because like I'm using OBS while recording this, but the average response time is a lot in this case when the number of users like keeps increasing. Uh, I can also showcase the failure and recovery part in this example where I failed 4 nodes this time, and in this case you will see that uh, this makes like a great like sort of a like triangle or a parallelogram where these nodes are down, so there won't be any messages increasing. These two analyzers are up, and when I switch them back on, like all the packets will be equally routed to these nodes until they reach the amount that these two analyzers currently are at. I switch them back on, and right now we should have the parallelogram forming. Yeah. So in case of 1:1:1, 4 nodes that were down came back on, and like it wasn't that a single node was assigned all the packets, then a single node was assigned all the packets. The ratio was also followed when we were like bringing them back to the ideal distribution. So the load was distributed for the nodes that failed and came back. That's what I'm trying to say here. Right. So this was the test that I wanted to do for like high number of users and like a very high hatch rate with a ratio of 1:1:1 to showcase this result. Next, I am going to be running a test, not using locust, but using JMeter like to show what's the maximum number of requests per second that we can do in this particular application. Right. So I have provided a test plan with the repo that can be used to test JMeter. It's here. So to test using JMeter. So yeah, this is yeah, let's do 10,000 ramp up period. 1,000. Just what's the maximum number that I can think of? But yeah, I'll start this test. Yeah, and okay. Hi. So it's me again. The test has been running for a while, and this is sort of a good. There's a good thing and a bad thing that's going on here. The good thing is that the throughput that I'm at is like 3,800 requests per second. The bad thing that I just noticed is that my routing algorithm, like or the server, takes a long time to catch up to the ratio if it is put under very high load. So the thing that I observed here is that analyzer 5 was left behind analyzer 4 in ratio, and it is taking a long time to catch up uh, to its actual place in like messages analyzed. And the reason for this, I think, is that my global state with the uh, like with the shared memory that contains the number of packets assigned per analyzer is slow to catch up under high loads. This means that the concurrent data structures that I'm using in the server, when there is like extremely high load on one particular key, they take longer to update. Now, this is just my hunch, which I will verify in due time with the project. But yeah, that's the result of the high throughput test that I wanted to show. Now, there is also an interesting behavior that happens when I stop the load. It's that the the rate at which messages get assigned to each analyzer slightly increases. So you can observe that the slope of this graph here is going to change significantly. Yeah, there's a clear difference in the graph where in the slope here and the slope here, and that's something I wanted to show in this test as well. One more key thing to notice here is that even after I have stopped the load on the distributor, the messages are still being assigned, and this proves that the mailbox has like a lot of messages that weren't routed under the load. So now the distributor is trying to like clear the mailbox with all the requests that are still pending. Yeah, so those were the tests that I wanted to show. I also tried to explain why my system was showcasing the behavior that it was showing. Uh, and now I'll try to like explain the architecture and a few things regarding the service. So this is the architecture of my system. We have like a load testing service that's supposed to be like a log emitter service, which emits log packets with a random number of messages in between in those packets to the distributor. Then the distributor service, its job is to route the packets to different analyzers, and the routing algorithm should follow weighted distribution. So let's say one analyzer has weight 1 and one analyzer has weight 2. Yeah, two messages should be routed to analyzer 2, and one message should be routed to analyzer 1. Right. So in my architecture, I have JMeter or Locust for the high throughput load testing service, or like to simulate the log emitter. I have built the distributor using an Akka HTTP server. I used Akka because Akka allows me to use the actor model to like abstract out details about concurrency. So in this case, I have a main actor that receives the request. I have multiple worker actors. In this case, I used 100 worker actors. Uh, every time distributor receives a request, it sends a message to one particular worker, and then it's that worker's job to route the log packet to the proper analyzer. Now the workers share a shared state, like a global state, which is a singleton class. I have used concurrent data structures in this shared state, so it's lock free. Uh, the workers use this shared data to keep track of the number of messages that is assigned to each analyzer so far. And I also created a front end dashboard so that we can control the whole simulation to load test the distributor and to see how the messages are being routed to the analyzer and to like make sure that the failure and recovery system is working as coded. So the front-end dashboard, that's a React TypeScript app. I use ShadCN for the components. Yeah, it's a standard React app. And ray charts for the graphs that you see on the front end. So yeah, that is mostly about the architecture. Now the assignment had a few tasks. So there was a task which was define a data model for log messages log packet. I have defined this data model in both like my distributor and the fast API app. I'll show it in the distributor. So like a log message has level and message. The log packet has ID timestamp and a list of log messages. Very simple data model. Then I had to develop a multi-threaded web server that accepts a post request for a log packet. Yeah, this is the multi-threaded web server that accepts a post request for a log packet. It's the distributor app. Now, like you won't be able to see the multi-threaded part about the server because that's abstracted out by Akka. But as I said, it uses the actor model for abstracting out concurrency, but is highly concurrent, uh, which is like it has multi-threading and parallelism as well, which is managed by Akka. Design the logic for high throughput non-blocking thread safe distribution. Yeah, I used a global state with uh, not like data structures which are lock free or like use minimal amount of locks. It's the try hash map from scala.conf. Yeah. And it is like high throughput because in the test screenshot in README, I show that the system can do 5,000 requests per second using JMeter when I'm not recording using OBS, or 1,800 requests using Locus, which is like integrated into the front end. Set up a working demo. Yeah, I showed that. Handle the condition of one or more analyzers going offline for a while, then coming back online. That I showcased this in the failure and recovery part in the demo video. Uh, yeah, and right, yeah, there is also a one-page write-up where I talk about what other conditions I would have handled or like improvements. Uh, that's like one idea I had where I wouldn't use a global state and like let each worker just have their own local state and handle the ratio distribution based on the local state. And eventually, if all the workers handle the ratio, then yeah, the global ratio is also handled. So then we don't have to share state among the workers. So there are ideas like this in this particular document that I have written. The tech stack, yeah, Scala, Akka for the distributor, Python and Fast API for the analyzer, React TypeScript for the front end, Locust for the load testing service, and Docker Compose to compose everything up. Now, to just to reiterate on the testing results from the previous test that I did. So Uh, this test shows that like if the service is high throughput, uh, this test basically shows the failure and recovery testing part. I have like created this diagram where you can see the normal functioning on the graph, the when the node failure is simulated and when the node is back on, how the analyzers behave, and then how the ratio is brought back to where it should be again. So this is for 1:1:1 all nodes. This is for 1:2:3:4:5:6 for those six, and it also follows the same, where in normal functioning, both the messages per second and messages per analyzer follow the distribution. When the node failure is brought into the system, the remaining nodes follow like the new distribution. And then once the node are put back on, they try to recover using like different rate of message assigning. And then at the end, what I showed is the throughput with concurrent requests, where when there are users still hashing or when there is high load, the server has to deal with like dealing with the high load and also dealing with like routing the packets. But once the high load is brought to like a normal rate, the server then routes all the messages correctly without failing any requests. The requests they are still put in like a queue and processed one by one. Yeah, that's it, I guess. Thank you for watching.